Hello, we are Group 1. Our objective was to design and build a combined pulse rate meter and oximeter complete with a transducer, biasing circuitry, signal conditioning circuitry, and a digital display. I will describe to you the input gathering portion of our pulse oximeter. Here is a picture of the finger clip of our pulse oximeter. It has a red LED and infrared LED on the top and a photosensor or phototransistor on the bottom of the clip. The LEDs shine light through the consumer's finger and is detected by the sensor. Then, the sensor's data is sent to the amplifier circuit of our pulse oximeter.
Okay, so the goal of the circuit was to amplify and filter the signal that came in from the photosensor. First of all, we have a virtual ground so that we can use one power supply. After that, we have, with the rest of the circuit, we have a coupling capacitor that blocks the DC content and lets the AC content go through. Then that first little part of the circuit is the differentiator amplifier, which amplifies the signal, acts as a preamplifier, and also acts as a high-pass filter to let things above 1 hertz go through. After that, we go into an active low-pass filter, which lets low frequencies below roughly 3 hertz go through and attenuates everything else and has a gain of 1. Then finally, we go into our final amplifier, which also acts as another low-pass filter and also amplifies the signal one final time.
I'm going to be talking about how the microcontroller is programmed to calculate the pulse rate and oxygen saturation. The MSP430 is programmed using 2 sections of code. The first section uses timers to count the peak values of the signal. This value is incremented every time a peak value is recorded, or in other words, when a pulse is measured. This value is finally scaled to output the pulse rate in beats per minute. The second half of the code is for the calculation of oxygen saturation. In this section, we want to compare the intensity of red light versus the infrared that passes through the finger. The 10-bit analog to digital converter of the MSP430 is used to store 10 different digital values of the signal. These values are then averaged to calculate the average intensity. We then take a ratio of these two light signals and plug it into a linear saturation model. This will give us the percentage oxygen saturation.
For our pulse oximeter device, we use the Adafruit 16x2 LCD display that contains 16 different pins. We programmed the LCD by using a header file that contained function declarations and macro definitions for our main code. In the header file we declared the data pins of the LCD that would be connected to the MSP430, and we had 4 different main functions: the LCM set cursor position, clear LCM screen, initialize LCM, and print string. The LCM set cursor position was used to set the row and column for each character that would be placed in the LCD. In the clear LCM screen, we cleared any characters that would be displayed on the LCD. In the initialize LCM function, we set and initialized the values that would be obtained from the pulse oximeter, and in print string, we used this to print specific characters onto the LCD screen.
Talking about the hardware, a 9-volt battery was used to run the amplifier circuit. A 5-volt regulator was used to form a 5-volt rail that would power the MSP as well as the LCD. The 4-bit LCD mode was used so that we could save more GPIO pins as compared to the 8-bit mode. There are altogether 16 pins for the LCD display. The pins 4 and 6, RS and EN, are connected to 2.2 and 2.3, and the 4 data pins D4, D5, D6, and D7 are connected to the corresponding 2.4, 5, 6, 7 and pins of the MSP430. 2 pins goes to the 5-volt, 7 pins 1, 5, 7, 8, 9, 10 and 16 goes to the ground, and 1 pin, the pin 3 of the LCD, goes to the variable resistor for the contrast. The print string function was used to display the integer and convert to the character in the LCD.
Alright, so in order to start the measurement, you need to place your finger exactly in the middle where it aligns between the sensor and the LEDs. Once you have it aligned, you go back to the device and press the start button, which is this switch over here. Alright, so it's now measuring your heartbeat, and we can also look at the progress using this green LED. It changes every time it records a heartbeat. So now at this point it's actually measuring the oxygen saturation level. Now as we can see, we have a pulse rate of 88 and oxygen saturation of 95%, and these are the expected values that we expect from a normal human being. Alright, thank you. Alright, in this video I want to talk about a few limitations of this design. In our clip, the phototransistor and the LEDs aren't perfectly aligned. So the adjustment of your finger really matters. You have to position your finger at the exact center of the LEDs and the sensor for the best results. One other limitation we have is when we start the device, we might see something like this. And to fix it, we just have to reset our device a couple of times. Yep, till we get the right answer.